We're going to graph and analyze the rational function from example 1b in notes 4.2, day 1. So we're going to begin by factoring the rational function. The denominator is a difference of squares, so it can be factored as x plus 2 times x minus 2. To find the x-intercept, we're going to look for values that make the numerator equal to 0, but the denominator not equal to 0, otherwise it would be undefined. In this case, the x-intercept occurs at 0, 0, and that x-intercept has even multiplicity because the x and x squared occurs twice in the numerator. Next, let's find the y-intercept. The y-intercept we find by evaluating f of 0, letting x equal 0. So the y-intercept occurs at f of 0, which is 0 over negative 4, which is going to give us the ordered pair 0, 0. And whenever we have an x-intercept at 0, 0, we will also have a y-intercept at 0, 0. Next thing we're going to look for is vertical asymptotes. So vertical asymptotes occur when the denominator is equal to 0, but the numerator is not equal to 0, or if they're both 0, then it's a factor that we cannot cancel out from the denominator. In this case, we're going to have two vertical asymptotes, one at x equals negative 2 and one at x equals 2. They both have odd multiplicity because those factors occur once in the denominator each. So x equals negative 2 and x equals 2, and they both have odd multiplicity. In terms of wholes, we are looking for values that make the numerator and denominator both 0. So wholes, we have no common factors between numerator and denominator, so we have none. So no wholes here. Infinite asymptote, we're going to look for values that make, we're going to compare the degrees of the numerator and the denominator. So infinite asymptote, here the degree of the numerator is 2, the degree of the denominator is 2. Since n equals d, we have a horizontal asymptote. Its equation is the ratio of the leading coefficients, which is 3 over 1, which is 3. So we're going to have a horizontal asymptote at y equals 3. We will not have any slant asymptotes. We can't have both. In terms of intersection, we're going to look for values where, I'm going to squeeze it in here, 3 is equal to 3x squared over x squared minus 4. So this is for intersection. And if we multiply both sides by x squared minus 4, we're going to get 3x squared minus 12 is equal to 3x squared. That has no solution. So we have no points of intersection between our graph and our infinite asymptote, which is the horizontal asymptote y equals 3. To sketch the graph, let's put on our x-intercept, and that's also our y-intercept. In this case, I'm going to put a little e next to it because it has even multiplicity. Let's sketch in our asymptotes. We've got the horizontal asymptote at y equals 3. So I'll sketch that using a dashed line. Y equals 3. And then I'm going to put on the vertical asymptotes at x equals negative 2. I'm going to put the equation x equals negative 2. I'll put a little o by it because it has odd multiplicity, and we'll also put in the vertical asymptote at x equals 2. And also a little o because it's odd. And from this, we have enough information to sketch our graph. How we're going to do that, we're going to put the pieces of the puzzle together. Let's begin with the point that we know. This x-intercept, which has even multiplicity at 0, 0. We know that our graph cannot cross the horizontal asymptote. And we know that our graph needs to bounce off this x-intercept, in which case it would either be going up or downwards. Since we can't cross this horizontal asymptote at y equals 3, we did the analysis here that shows we have no points of intersection. That means that our graph has to look kind of like what we might think looks like a little bit of a parabola, but it's not, but that sort of shape in between the lines x equals -2 and x equals +2. Next, let's think about what happens when we move to the right and cross the vertical asymptote at x equals 2. This is a vertical asymptote with odd multiplicity. That means when we cross over this vertical asymptote, where our graph is going to go across the x-axis, and the ends of our graph are going to shoot in opposite direction right here. So if it was going down here, it's going to be shooting upward when I go across that vertical asymptote. We also know that our graph can't cross this horizontal asymptote from our analysis. So as x goes to +infinity, our graph is going to get closer and closer to the horizontal asymptote at y equals 3. Now let's see what happens when we go across the vertical asymptote at x equals -2. This has odd multiplicity. That means if we're shooting down here, we're going to be shooting up on this side because it has odd multiplicity. And once again, we cannot cross that horizontal asymptote because of our analysis. And as x goes to -infinity, the graph is going to get closer and closer and closer to the line y equals 3 along this branch.